Hello everyone, welcome to this episode of Geospatial Solution Training brought to you by DJI Enterprise team. This is Ron Lee from Solutions Engineering team. And in this episode, I'd like to talk about scale factor. Before we start our episode, I'd like to recommend you to go through the previous episodes, especially the ones on the coordinate systems, so you can better interpret the content from this episode. All right, let's get started. First, let's have a look at the content page for this episode. First, I'm going to talk about the scale factor, telling what it is, and then same thing for the elevation factor, and combining two that give us the combined scale factor. I'm going to explain what these factors are and why are these important, and then talk about why shall we apply scale factors for some use scenarios, and also talk about how do we actually apply these scale factors. Let's start by discussing the scale factor. The scale factor is a correction factor used to rectify scale distortion caused by projection. As discussed in our previous episode on the horizontal coordinate system, we have covered that the geographic coordinate system, which uses the ellipsoidal shape to interpret the Earth's surface, can actually be converted to multiple projection coordinate system based on the projection method. So I'm going to take one example, which is the UTM projection, to kind of explain what scale factor is. So in this example, a portion of the Earth's surface is projected on a cylinder. The Earth is effectively flattened from north to south during this projection process. And on the diagram, two intersecting lines, which is AB over here, DE, that's the second line, DE. Now these two intersecting lines actually touch both the Earth's ellipsoid and the cylindrical shape used for projection. So along these two lines over here, the scale factor is actually 1 because there's no distortion. However, as we move towards west or east side of these two intersection lines, the distortion starts to increase. And we can see this better if we have a look at the intersection view from the equator, which is this diagram over here. And if I correlate from my intersection view to the actual diagram, the AB line will simply be that point over here because we're looking at the intersection view from the equator. The E line over here, that will also be intersected here. And along this part again, the curvature from the ellipsoid surface touch the projection surface, which is the straight line over here. So these two intersections, there will be absolutely no distortion. But as we move from the west to the east further, let's say if we have a measurement over here, which is AB, regardless the elevation for now, let's have a look at the length of the AB compared to AB on the projection surface. You'll notice that the ellipsoid measurement over here is actually longer than AB measurement on the projection surface. And this is because of that distortion. Now, to correct that, you will need to apply this scale factor. And that scale factor will be less than 1 because you have to multiply the scale factor to the ellipsoidal surface, which in this case AB, in order to get the measurements on the projection surface. And similarly, as we're moving toward the east side of this intersection and west side of this intersection, you will notice that the ellipsoidal surface is actually beneath our projection surface. And the result of having that is our measurement from the ellipsoidal surface is actually going to be shorter compared to our measurements on the projection surface. So when that happens, you will need to multiply a scale factor that is greater than 1 to compensate that distortion and to get your measurements correct. So over here, I also have the map of Kansas, which is in UTM projection as well. This shows the linear distortion among the area of Kansas from the UTM zone. And as you can see, similarly, we have these two green lines, or green zones in this case, over here and over here. That indicates the intersection lines. And among these green region, you're going to have minimal distortion. And if we move slightly toward west or east, you can see that distortion increased. So in this example over here, if we have a scale factor k, you will need to multiply k to the ellipsoidal measurement in order to get the distortion corrected projection measurement. And since now we all know that there are multiple methods for doing projections, depends on the method you used for gathering these projection maps, the scale factor can be calculated differently. Also, since the Earth is not perfect ellipsoid, in the actual world, you're going to see elevation difference, which would also affect your scale factor. Overall, the purpose for having the scale factor is that you can easily convert from grid measurement to ground measurement. And it is important because some project would require deliverables in grid scale measurement. So when those requirements appear, you will need to consider applying the scale factor. Usually they're given based on the region. Let's now talk about the elevation factor. So in addition to scale factor, there's also elevation factor, which takes account of the actual elevation on the ground surface and take that into consideration to further correct the distortion. Over here, I also have a diagram to show you how that works. So over here, that's the center of the Earth, and this distance over here basically is the approximate radius of our Earth based on the shape of ellipsoid. And this dashed line over here, which shows the curvature line, that is our ellipsoidal surface. And this linear line over here represents the projection plane. So when we have a look at the measurements from this point to this point, down to the projection measurement from this point to this point, you can see that the distance is going to be longer. So it has to apply a scale factor that is a little bit less than 1, so 0.999 something, in order to get the correct measurements from the projection plane. However, as we all know, the Earth is not perfect ellipsoid shape, so you're going to have a mountain and hills. So based on the actual ground elevation, your elevation might be here, and your measurement may start from there. And as you can see, as you increase your elevation height, there is going to be an additional elevation factor that also needs to be applied in order to correct that distortion caused from the elevation changed. So over here, as you can see, if I measure from the actual ground surface here to here, now not only I need to apply the scale factor, I also need to apply the elevation factor based on the elevation difference from the ellipsoid surface to the actual ground distance. So how do we get the elevation factor? The calculation is over here. Basically, you have the approximate radius from the ellipsoid model, then you divide the radius plus the average height difference, and that would give you the elevation factor. And you probably notice now at lower elevation regions, it may have minimal effect because your elevation is low. However, when you're working, let's say in mountainous area, you would be affected. So over here, I have a chart to indicate that. For example, if that height difference is going to be only 10 meters, the impact on the elevation scale factor for every 1,000 meters on horizontal distance, you're only gonna get 0.002 meters in terms of error caused from the distortion. However, if I increase that distance to 1,000 meters, elevation to 1,000 meters, I'm starting to get some noticeable errors due to the distortion. So this is another factor you need to consider when applying to correct the distortion caused from projection, especially when your project is located at high elevation area. Now, by knowing what the scale factor and elevation factors are, you probably guessed it what the combined scale factor is. And you're right, it is basically combining the scale factor and the elevation factor. And that gives you the combined scale factor. So on the right side, I have a map of the Colorado state showing the linear distortion. Like we all know, we are expecting distortion, and different color indicates a different level of distortions. And we can kind of see the central line indicates where the area is being projected. And we also can see these green lines over here, which is similar to the UTM projection we had, which these are the intersection lines, or the area has the minimal effect. As you can see now, due to the elevation changes and difference, it's not going to be a perfect rainbow shape. And these distortions are not evenly distributed because of the elevation. So now you're getting the difference or the scale factor, which you need to apply for correcting the geodetic distance to the grid distance. In addition, correcting from ground distance to the grid distance by adding the elevation factor, or applying elevation factor to be exact. And that gives you the combined factor, which is the factor you need to apply. So over here, the equation shows you the combined scale factor is equal to grid scale factor multiplied by the elevation factor. And the grid distance is equal to combined scale factor multiplied the ground distance. Okay, now let's talk about why does the scale factor matter. First of all, it would help you maintain the accuracy across the entire project. If you have a large project, especially cross-state projects, applying scale factor effectively would make sure your measurement is accurate. And sometimes, due to the regulatory compliance, it is a requirement for certain projects to apply a given scale factor to your measurement, so all the measurements are comparable. And thirdly, and most importantly, it would ensure the local accuracy and ensure your measurement accuracy is reliable and precise. This is essential for accurate geospatial surveying projects. And because this episode only tend to get you to understand the concept of the scale factor, which scale factor you should be applying is really depends again on which projection you are working with. And some states would provide you scale factors for you to work with based on the region you are located. Other states, on the other hand, may not require you to apply scale factor, but to ensure the accurate measurements on the ground surface, especially for those states at high elevation, you would probably want to apply scale factor, ensuring your output result is measured correctly. On the right side, I have two map which shows the same Kansas state, but under different projection. As you can see, the linear distortion is completely different based on the type of the projection you work with. So knowing your projection first is important for you to apply the correct scale factor in your project. So how do you actually apply a scale factor in your drone project? There are multiple ways for doing this. First of all, your drone data was initially collected from a geographic coordinate system. All the data you capture that is geotagged with geographic coordinate system coordinates, which is longitude, latitude. And while you're processing these data and outputting whether a ortho map or 3D model, point cloud, these deliverables can be converted into a desired projection format, which is in XYZ. And when applying scale factor, you simply need to multiply these numbers to gather the final results in a projection format. Or you can also do a local coordinate system transformation. By doing this, you basically doing a transformation and getting your deliverable in a projection system that is in local or custom made, which in this case, it's already scale factor applied. But that would actually require you to have 3 or more sets of points, and each set of measurement would require the coordinate in a format of WGS84 and ellipsoidal height, then the XYZ. If you have that information, you can perform the 7 parameters transformation directly in Terra and output your deliverable into a coordinate system that takes the scale factor into account. Or you can also apply scale constraints. Basically, you can apply constraints to scale your drone data measurements visually, matching up with the actual world measurements. By doing that, you will warp your model and make sure the measurement match with the real world measurements, and that way you can get your ground measurements without applying a scale factor. Okay, with that being said, that's everything about this episode on the scale factor. The scale factor may not apply to your project based on your elevation and scale of the project, but it's definitely something you need to kind of take in consideration, especially when it comes to measurement, because overall it's going to affect your results if you're not properly apply it to some projects. That's everything about this episode, and I will see you in the next one.